All right, let's just dive right in. Today, we're going to try and wrap our heads around one of the biggest, most ambitious, and, well, let's be honest, most mind-bending ideas in all of physics, M theory. This is really a journey to the absolute edge of what we know, all in the search for a single, beautiful explanation for, well, everything. But before we get buried in the math and the dimensions, let's start with something a little more poetic. Just think about this for a second. What if everything you see around you, I mean everything, from the tiniest speck of dust to the biggest galaxy, is actually just a different note in some grand cosmic symphony? Just hang on to that thought because it's really the heart of everything we're about to explore. So why do we even need a wild theory like this in the first place? Well, it turns out that for nearly 100 years now, physics has had this huge, glaring problem sitting right at its core, a deep, fundamental conflict between its two greatest theories. On one hand, you've got Einstein's masterpiece, general relativity. This is the rule book for all the big stuff out there, planets, stars, the whole cosmic dance. It describes gravity as this beautiful warping of space and time. Then, on the other hand, you have quantum mechanics, the incredibly successful, but, let's be honest, super weird set of rules for the tiny stuff. Atoms, particles, all that. And here's the kicker. They don't play nicely together. They are completely incompatible. When you try to use their equations at the same time, like to figure out what's happening inside a black hole or at the exact moment of the Big Bang, the math completely falls apart. It just spits out nonsense, literally infinities. Gravity, the way Einstein saw it, has no place in the quantum world. And that is the problem that has kept physicists up at night, searching for a single theory of everything. Okay, so that's the problem. And that's where this totally radical new idea comes in. An idea that started bubbling up back in the late 1960s. It proposed to solve this whole mess by changing our most basic idea of what reality is even made of. String theory says that if you could zoom in on something like an electron, way, way closer than we could ever possibly see, you wouldn't find a little dimensionless dot. Nope, you'd find a tiny, vibrating little loop of pure energy, a string. In this picture, every single fundamental particle is just one of these little guys. And this is where that whole symphony idea really comes to life, right? Think about a guitar string. It can vibrate in different ways to make different musical notes. Well, these fundamental strings do the same thing. One particular vibrational pattern makes the string look like an electron to us. A different pattern looks like a photon. But, and this is the amazing part, the real aha moment for physicists, one specific vibration had the exact mathematical properties of the graviton, that particle of gravity that they had been looking for. It wasn't something they had to cram into the theory. It just popped right out of the equations, naturally. So for a minute there, it really looked like this beautiful idea might be it, the answer. But as physicists kept digging into the math, they realized the story was about to get a whole lot more complicated. It was about to splinter. Problem number one was a big one. The math for string theory only holds together, it's only consistent, in a universe with more dimensions than the four we know. 3 of space and 1 of time. Specifically, superstring theory needed a universe with 10 space-time dimensions, 9 for space and 1 for time. So, where are they? Where are these other 6 dimensions? Well, the main idea is something called compactification, and the best way to think about it is with a garden hose. From really far away, it just looks like a line, right? One-dimensional. But when you get up close, you see it has a second dimension, the part that goes around the hose. The thought is that the extra dimensions of string theory are curled up so incredibly tight, on a scale so tiny, that we just can't perceive them in our everyday lives. But believe it or not, the extra dimensions weren't even the biggest headache, because as researchers kept exploring the math, something really frustrating started to happen. The quest for the one single unified theory. Well, it wasn't one theory anymore. There were 5. And this was a real crisis for the field. I mean, how can you have 5 theories of everything? That kind of defeats the whole purpose, right? You had these 5 totally consistent but different versions of superstring theory. Each one needed 10 dimensions, but they all worked a little differently. It looked like the whole beautiful idea had just fractured into a complete mess. And right when it looked like the whole idea might just collapse under its own weight, something amazing happened. A breakthrough that kicked off what physicists now called the second superstring revolution. So throughout the early 90s, physicists started noticing these strange mathematical links called dualities that connected these 5 supposedly different theories. It was like discovering that 5 completely separate languages were actually just dialects of one single ancient language. Then, in 1995, at this huge string theory conference, a physicist named Edward Witten gets up on stage and basically changes the entire game. What he proposed was that these weren't 5 separate theories at all, they were just 5 different ways of looking at one, even bigger, even more fundamental theory, one that exists in 11 space-time dimensions. He called this overarching framework M-theory. You could think of it like this. Imagine looking at a mountain from 5 different spots. You'd get 5 different views, and they might look very different, but it's all the same mountain. That's the idea here. So what does the M in M-theory stand for? Well, Witten himself has always been a little playful about this. He said it could stand for magic, mystery, or membrane. That last one, membrane, is because the theory isn't just about 1D strings anymore, but also these higher dimensional objects called branes. The fact that the name itself is still a bit of a mystery kind of tells you how much of this is still an unknown frontier. Okay, so this sounds incredible, right? A theory of everything in 11 dimensions. The search is over? Well, not so fast. We have to be really clear here. M-theory is not a finished product, not by a long shot. It's a work in progress, this gorgeous mathematical idea that's full of promise, but also faces some enormous challenges. And the hurdles are huge. First off, we have never, ever detected any of those extra dimensions. We also still don't even have the complete equations for M-theory itself. We're just working with pieces and approximations of it. But the biggest challenge of all? There is absolutely zero direct experimental evidence for any of this. The kind of energy you would need to actually see one of these strings is it's astronomically beyond anything we can possibly build today or in the near future. And so we're left right back where we started, really, with a massive question. Is M-theory a true glimpse into the ultimate fabric of reality, or is it just a beautiful piece of mathematics that happens to lead nowhere? For now, we simply don't have the answer. But it does leave you wondering, doesn't it? Is it possible that we are all living our lives as just one intricate melody in a vast 11-dimensional cosmic symphony? The search continues.